Now we're going to talk about a specific kind of motion, constant acceleration. So we've seen the derivative relationships between position, velocity, and acceleration. And we've seen cases where the acceleration is some function. So let's think about two different acceleration functions. You might have one acceleration as a function of time is 5t squared. Okay, and another function describing an acceleration is -6. Okay, well, for different time values, this first one is changing. You know, like for time equals 1, you have one acceleration. For time equals 5, you get a different acceleration. And so this is not constant. This, though, no matter what time you choose, the acceleration is the same. And so that's an example of constant acceleration. And this is the kind of motion that we're going to be talking about here. And the reason we talk about constant acceleration is because there are a lot of cases that are important to us where acceleration is constant. And so being able to say something about this is useful to us. So in order to come up with the equations for constant acceleration, I'm going to go back to thinking of an object that's moving. So this object has acceleration, velocity, and position. And as this object is moving, a stopwatch is tracking that as time goes by. And so remember, I am going to think of like the start of the motion, and that start of the motion is when we click the start button on the stopwatch. Okay, so at the start of this motion, we click on the start button, and the stopwatch says zeros, but now the time is going to start counting up. And for all of these calculations, here is what we're going to use in our calculations. At this instant that you turn the stopwatch on, our time is equal to 0 because that's what the stopwatch says. Our position is also going to be equal to 0 because, like I said, when we were talking about the relationships between position and time, we're just going to put the 0 of our number line wherever the object is when we turn the stopwatch on. So this is also going to be 0. And then the new thing that we're going to introduce is the velocity. And the velocity at the instant that we turn the stopwatch on, we're going to call lowercase v sub 0. Now, as time goes by, let's think of a later instant. We're just letting this stopwatch run as the object moves. And now the stopwatch is going to say some other number. It's not actually going to say t, but this t is going to represent whatever number it says. Okay, so that might be 50.67 seconds or something. But the time at that instant then is going to be whatever that value of t is. The position at that later instant is going to be p, and the velocity is going to be v. Okay, so you have to know that v sub 0 is the velocity when you turn the stopwatch on. The v without the sub 0 is the velocity at some later instant t. What's the acceleration? Well, we don't have separate accelerations at these two, because at both of these two instants, since the acceleration is constant, it's going to be the same, and we're just going to call that A. Okay? So in a case like this, there are three important equations that we're going to use to come up with relationships between these variables. And those are, the first one says that the velocity at time t is equal to the velocity at time 0 plus a times t. The second one says the position at time t is equal to v sub 0 times t plus 1/2 a t squared. And the third, last one says 2 times a times the position is equal to v squared minus v sub 0 squared. So these are the three constant acceleration equations. And now I'm just going to go through a few examples to show you how to use these to calculate things we might want. Before I do that, where do these equations come from? These equations actually come from, well, the first two of these equations come from starting by assuming that the acceleration function is just a constant a, and then integrating to get the velocity and using the initial conditions to find the constant of integration, and then do that integration one more time to get the position. And you can do all that. I'm not going to stress that. I'm not going to go through it. I'm not going to make you do it. But that's where it comes from. It's actually pretty simple calculus. And then the third one just comes from combining these first two. So it just comes from algebra after you've done that integration. Okay, so let's see how to use something like this. Okay, so let's say that a car starts at rest. And then it maintains a constant acceleration for 100 meters. And it travels these 100 meters in 4.0 seconds. And what we want to calculate is, first, what's the acceleration? Second, what's the car's velocity when it's, at the end of these 4 seconds, when it's traveled 100 meters. And third, we're just going to think about, do the signs of the velocity and the acceleration make sense? Okay, with what we know about velocity and acceleration. Okay, so I'm going to draw a little picture of what's going on. Here's the car going this way. This is the instant when we turn the stopwatch on. Okay, so this is our 0, let's say 0, 0 time. Okay. And so at this instant, our time is 0. When the car is, at the start of this motion, the time is 0. The position is 0. It's at rest. It says the car starts at rest. So at this instant, based on what we're given, we know that the velocity is also equal to 0. And then we want to figure out some stuff about what happens, as it goes this way. So over here, we know that this is going to say 4 seconds And we want to know what's happening with the car at that instant. Okay, well, let's think about what variables we know and what we're trying to find. So we know that, I mean, you can think about all of the possible variables that come up in these things. And they are t, acceleration, p, v sub 0, and v. That's all, just 5 variables. So let's list out which ones of these we know. At this later instant, we know that our time t is going to be 4 seconds. So I'm going to write t is equal to 4 seconds. Our acceleration, well, we're trying to calculate that. So I'm going to, over here, say what we want is the acceleration. The position, do we know the position when the stopwatch says 4 seconds? Well, we know it's traveled 100 meters. We know that this is the 0 of our number line. We have to choose a direction that we're going to call positive and one we're going to call negative. We might as well choose the positive to be the direction it's moving. You don't have to do that, but I think most people probably would, just sort of for convenience. And so when the car gets to this, you know, when the stopwatch says 4 seconds, the car is going to be at a position 100 meters away in the positive direction. That says that the position is going to be 100 meters. Okay, what else do we know and what else do we want? The position is 100 meters. The velocity at time equals 0. It said it's at rest, so this is going to be equal to 0. And then the velocity, we don't know that. Nothing gives us that. We're going to try to solve for that in part B, but for now I'm going to just ignore that and try to work with what we have here. Okay, so if you look at these 3 boxed equations, the question is there any one of these equations that'll let you solve for the thing you're looking for? In order to solve for what you're looking for, everything else in that equation has to be known. So let's see, let's think about the first equation. Let's just go through them one by one. So what about this one? Well, A is in it, so that's good. You can't solve for something that's not there. But V is not something that we know. And so we can't use this equation. So let's go on to the second equation that says P is equal to V sub 0 times T plus 1/2 A T squared. Can we use this equation? Well, A is there. That's good. T we know. That's good. V sub 0 we know. That's good. And P we know. So this equation is going to work. And so now I'm just going to plug these in. We have that 100 is equal to 0 times 4 seconds plus 1/2 times A times 4 squared. So 100 is equal to, this is 8A. And so A is equal to 100 divided by 8 is 12.5 meters per second squared. So that's the acceleration. That was the first thing that we were trying to find. What's the acceleration? Now we want to find the velocity after 4 seconds. So let's think again about what we know and what we're looking for. And we can just go through this list of variables Again, TAP V0V. We still know time is 4.0 seconds. Now, this time we know the acceleration is 12.5 meters per second squared. We just got that in part A. The P, we still know, is 100 meters. V sub 0, we're still turning the stopwatch on at that same instant, so this is still 0. And then the thing we're trying to find this time is V, the velocity at the time t. Okay, so is there an equation that we can use to find V? Well, let's just go through them from the start again. Let's think about this first equation. V is equal to V0 plus AT. Does this one work? Well, it has the variable we're looking for. That's good. V sub 0 we know. A we know. T we know. So this one will work fine. And we don't have to look any farther. So V is equal to 0 plus 12.5 times 4. And so V is equal to 50 meters per second. Okay. And then the last thing that I asked was, do the signs of velocity and acceleration make sense? Okay, well, what that means is we can tell from the problem usually, in this case we can, whether the object is speeding up or slowing down. In this case, it has to be speeding up if it's starting at rest. And so we expect the velocity and acceleration to have the same sign. That's required if something's speeding up. Okay, well, we calculated that the velocity is positive. We calculated in part A that the acceleration is positive. We know from reading the problem that this car has to be speeding up. And so these are consistent with each other. This makes sense. So let's do another similar example. Just keep getting practice with these. So in this one, let's say that, may as well just use a car again. Let's say the car is going 30 meters per second, and it hits the brakes. And stops over a distance of 40 meters. How long in time does it take for the car to stop? Okay, so I'm going to draw it pretty similarly to how I drew the last one. We're going to start the motion when the car hits its brakes. So this is the instant when we turn on the stopwatch. And then we know that it's a distance of 30 meters before the car gets to here. And this is when it's at time t. And we don't know that time. We're trying to find that. So I'm just going to write that as t here. Okay. And again, I'm going to make my positive direction the direction it's moving, my negative direction this way, But this problem would work out fine if you switched those the other way. Now we're going to think about, just like we did in this example, we're going to think about which of these variables we know and what variable we're trying to find. Okay, so first I'm going to list the variable t. This time we're not given that. That's the thing that we're trying to find. And now I'll go to the variable acceleration. We don't know that, so I'm not going to put that anywhere. The variable p, well, it says it takes 30 meters to stop, and it's going to be traveling in the positive direction. So if the car has traveled 30 meters in the positive direction from 0, this p is going to be 30. Next, what about the velocity at time equals 0 when you turn on the stopwatch? We know that. We know that the speed is 30 meters. Oh, sorry, I wrote this wrong. This should be 40 meters. Okay, the velocity is the one that's 30. We know that the speed is 30 meters per second. And then you have to think, do we know which direction it's going? In this case, we know the car is going in its positive direction. And so that gives us a value of positive 30. And then finally, do we know when the stopwatch says t, do we know what the car's velocity is? That's when it comes to rest. And so we know that v is equal to 0. Okay, do we have enough information to solve for t? Well, let's think of all of these equations one by one. So there's the first one. It has t in it, but it doesn't have a, so this one is not going to work. I mean, it has a in the equation, but we don't know what a is, so that one's not going to work. The second equation, p is equal to v sub 0 t plus 1/2 a t squared. Is this one going to work? It has t, but the problem is, again, this equation has a in it. We don't know what that is, so we can't use this one. What about the last equation? 2a times p is equal to v squared minus v0 squared. There's no real suspense here. Well, first of all, there's no t, so we couldn't solve for it anyways. But there's an a in the equation. We don't know a, so none of these are going to work. And so what are we going to do? Well, the thing that kept us from solving for t was that we didn't know a. So let's see if there are any of these equations that are going to let us solve for a, and then we can try again. There's only one equation that doesn't have a t in it, and since we don't know t, if we're going to solve for a, we have to use that one. So the only possibility is this. 2a times p is equal to v squared minus v0 squared. That's the only one that could work. And so let's go through. Do we know these things? A, we're trying to solve for. P, we know. V, we know. V0, we know. And so this should let us solve for A. And so we have 2a times p is 40. And that's equal to 0 squared minus v0 was 30, and we're going to square this. And so if you multiply this out, you get 80A is equal to negative 900. Now divide both sides by 80, and you get is equal to negative 11.25 meters per second squared. Well, now let's try again. So, now we can take this A and put that in our list of variables that we know and try this again. So what about this equation? V is equal to V0 plus AT. It has T in it. This time we know A, we know V, and we know V sub 0. So this one should work. Our V is 0. Our V sub 0 is 30. Our A is negative 11.25. Our T is what we're trying to find. And so 11.25 T is equal to 30. And so T is equal to 2.6 repeating seconds. We got a positive number for T, so that's a good sign because we're never doing calculations in this class with negative times. And then let's think again, do the signs of our velocity and acceleration make sense? I think this is always a helpful thing to do to avoid, sometimes you can catch mistakes that you've made this way. Well, is this car in this example speeding up or slowing down? In this case, the car is slowing down. It's hitting the brakes. And so we know that the velocity and acceleration have to have opposite signs. So let's look at what they are. Our velocity over the whole thing was, it ranged between 30 and 0, so it's positive the whole way. Our acceleration is negative, and so yes, it makes sense. This thing is slowing down, and our velocity and acceleration had opposite signs. For the last example, let's think about a ball rolling up a ramp. So this ball starts out with some velocity, and it slows down as it goes up the ramp until it briefly comes to rest and then starts rolling back down. And so let's say that this ball comes to rest, reaches its highest point 1 meter away from where it starts. And let's say that it starts rolling up the ramp. At 3 meters per second. So it reaches its highest point one meter up the ramp. And the question is, how long does it take? To reach its highest point? Okay. Well, when it's going 3 meters per second, that's the instant when we're going to turn the stopwatch on. So that's the 0. And then here, we don't know what the stopwatch says. It's going to say t, but that's going to be when it's gone up 1 meter. And our number line, I'm going to call this direction positive and this direction negative. And then the 0 is here. So our 0 position is going to be where the ball is when we turn the stopwatch on. And now we'll start thinking about what variables we know and what variable we want. Okay, we don't know how long it takes. That's what we're trying to find. We don't know the acceleration. The position at time t, we do know. That's 1 meter in the positive direction from 0. So p is equal to 1 meter. The starting velocity, we know. The speed is 3 meters per second. And then we have to think, is it moving in the positive or negative direction? In this case, it's moving in the positive direction, so this is positive. And then finally, do we know the velocity at time t when it reaches its highest point? And yes, we know that when anything reaches its highest point, it has to briefly come to rest before it goes back the way it came. So this is what we have. Do we have a way to find t? And in this case, we have the same problem we did in the last example. We don't know a, so we're going to have to use what we have to try to find a before we can do anything else. So I'm going to use the equation 2ap is equal to v squared minus v0 squared. So 2a times 1 is equal to 0 squared minus 3 squared. So 2a is equal to negative 9. And so a is equal to negative 4.5 meters per second squared. And now that we have that, that's one more bit of information we have that we can use to try to find t. So now, is there an equation that works? Yes, it looks like we can use v is equal to v sub 0 plus at. 0 then is equal to 3 plus negative 4.5 t. And so 4.5 t is equal to 3. And so t is equal to 0.6 repeating seconds. And now let's just think for a second about the signs of the velocity and acceleration and make sure those make sense. This ball is slowing down during the interval we're thinking about. The velocity is positive. It's between 0 and 3. The acceleration is negative. That makes sense because it's slowing down.